marker. Okay. Make sure that I.
Good morning, everyone. Today is the final day of ICNDA, and in this morning, we have a dedicated keynote session by Professor Kamrul Hassan. It is not an easy job to introduce Professor Hassan. Let me slowly explain why. Professor Kamrul Hassan, he is a senior professor in the Department of Physics, Dhaka University, Bangladesh. He did his PhD from UK and postdoc from Potsdam, Germany. His research area is statistical physics, complex system, theory of fractals, percolation theory, etc., etc. Apart from his dedicated research, he is engaged in several diverse activities. For example, he is actively involved in social working. He is influential in social network. He writes regular articles on the top newspaper of Bangladesh. He is working on the rights to the education for the kids, for the students, and for the young people like you. So really he is involved in several diverse activities. You know, what is an easy definition of a complex system? Don't worry, this is not my lecture. I am here to introduce only him. But complex system is a unit that has several interacting subunits working all together. That's why human body is a complex system. But think about human activity. If a person has several different diverse activities, then scientifically it should come with a proper definition. So here in ICNDA, I'm here to introduce a new metric called human complexity. It represents the amount of diversely different work done by one individual. And if you measure the metric for Kamrul Hassan, for sure it will keep increasing. So, my dear Kamrul Hassan, I wish your complexity curve in terms of time it remain increasing, and I invite you without any further delay to share your keynote here. Thank you very much.
Oh my God. Thank you so much, Santo. First of all, I would like to thank the organizers, especially my dear friend Santo and Osit Shah, who invited me to come all the way from Dhaka to be here to make my stay a pleasant one. I would like to thank also the team, the whole team, for making my stay really, really pleasant. I loved it. I have said it several times with so many others, many of you, that I love this campus. I'm deeply in love. The more I see, the more I love. And so that's all for now. The slide you see here, two of my co-authors, that book we have written together, Santo Banerjee is here, Gauri Shankar is here. So, and the one, Sam Mukherjee, who is not here right now. So, this book has been published in 2020. The title of today's talk is on understanding, mainly multifractal. So, I will propose a model, a lattice, which is multifractal, not only multifractal, but multi-multifractal. then it is also a scale-free network, and at the same time it is small world. Say in one system you will find all the things that you could find. So little by little I will discuss those. So, but my main focus will be on multifractality. Before I start discussing on multifractality, first I would like to say a few words about fractal. Okay, but before going further details, this talk will be like a full meal course. The apparatus will be a brief discussion about what is Euclidean geometry and what is fractal, so that you can appreciate what is fractal and what is not. And then antipasto, I will discuss the theory of the multifractality in detail. And as a first course, I will give the application of multifractal, a few applications which are deterministic case. And as a main course, that will be introduction to my model that I proposed in 2010, and still I am working on it. We discuss two of its flavor and its multifractal property, its scale-free property, and its small world properties. And as a dessert, I will summarize the talk. What is Euclidean object? In fact, to understand what is fractal, it is indispensable to understand what is not fractal. And what is not fractal is Euclidean geometry. There is a history of describing geometry objects that we see around. Pi geometry is as old as science itself. It has always involved the Euclidean geometry that has restricted the boundary of our imagination to line, parallelograms, semicircles, circles, parallelepiped, spheres, cylinders, etc. What is the common feature about them? If you increase the linear size of the object, the mass increases in this fashion. For instance, if we have a line, then say a line of 1 meter, if you double it, mass will also be doubled. If you have a square, it will, if you double the linear size, mass will increase by 4 times. So that is the relation, mass length relation. The next thing that I want to define is called density. What is density? There are two things here. Mass of the object and the volume of the space where the object is being embedded. So if you put the mass, in this case, both scale by the same quantity, and hence, since d and d cancel out, it means that density is constant. So now you can picture what is Euclidean object. If I give you a bag full of points, identical points, and I ask you, make a line, what would you do? You put them uniformly, making sure the density is constant. If I ask you to make an object which has dimension 2, how would you decorate them? You would decorate them in a fashion so that number of points per unit area remain the same. So it is the uniform, isotropic distribution of constituents of the object. If it is so, then we call it Euclidean object. But there were many objects in nature we see around. They were known as a monster. From the geometric point of view, they were known as a geometric monster. Till 1975, when Manipal, for the first time, introduced the idea of fractal. So what are those pictures? How do they look like? You see one thing here, D assumes the value 1 for one-dimensional object, 2, 3. When we were in the school, we were given the definition. An object is called one-dimensional if it has a length, two-dimensional if it has length and width, and so on and so forth. While we came to the university, we studied linear algebra. We came to learn that if the points of an object, to describe the points of an object, if you need two linearly independent axes, the object is two-dimensional. Or three linearly independent objects axis, then three-dimensional. Is that okay? But there are objects like these. They don't have integer dimension. We never question ourselves that is there objects which may have dimension between 0 and 1, 1 and 2, 2 and 3. If there are, then how do they look like? That was the kind of questions that Manipal asked. And he also found the answers. So these are the objects. If you increase the linear size, mass increases, but exponent d is no more integer. But one property they have common, and that is called self-similarity. What does it mean? If you blow up the part, if I take a part of it and take a picture and then I magnify it and I show it to you, it's the whole thing. So part look like in the whole. So it is called self-similar. So an object, which all these objects are self-similar, but to understand whether they are self-similar or not, you need a special tools. For Euclidean object, even a child can know that if you take a line, if you take a part, if you blow up, it will look like the same as a whole. So Euclidean object is also inherently self-similar. But to know that these things are self-similar, they are statistically self-similar. Some things are called strictly self-similar if you are making it in a deterministic fashion. But nature doesn't grow things in a deterministic fashion. So these are the objects. So this is dielectric charge and discharge, and then snowflakes, DNA, diffusion limited aggregation process, they create this kind. So in fact, nature is full of like this. Now, question is, how do we measure the dimension? So one way of measuring the dimension is called famous box counting method. What do you do? So if you have an object like this, you put a grid of linear size of the square and then measure how many square of this grid contain these objects. Even if a tiny bit of it is occupied in a box, you count it. So you count the number of squares, and as a function of linear size of the grid size, square size, and then you plot them in a log scale, you find a beautiful straight line. So this board, to measure the dimension of this board, you take a small square and you measure how many of this square do you need to cover this board. And then you make a smaller square. So you tune the value of R, size of the squares, and then measure obtain the number, and then take the log of the log plot, you get a straight line. In this case, you'll find the slope is 2. And in this case, I found the slope is 1.415. So that is the dimension. That contains even the smallest amount of this object. So I am not giving any extra favor if a square contains a large amount of this object. So that is not fair. There comes the point about multifractal. In fact, multifractal description is a generalization of the fractal theory. So I will now go on to the theory of multifractal, because that is the most important and generalized version of it. If you have a question, please you can raise any time if you want. Just stop me. Now, yeah.
mentioned we need to measure the size of small boxes and we have found it. Why not simply counting the rectangle size?
Rectangle size? Which one?
Yes. As you mentioned, this is the object and you are basically trying to fit by a box. So why we are going for a small box and why not simply counting the area of rectangle?
Area of the rectangle, you can do that because they are all the same area and the number will be proportional. Will give you the same value.
My question is why we are going for the small boxes? Why not for bigger boxes?
Bigger box, yeah. I started with even bigger. I say that you can tune the value of R. But if you are making it too big, then fine details will not be captured. The smaller you take, the finer details of the object are captured. So it's better to take smaller.
A bigger box may be missing some
Information will be lost.
Yes.
Yeah. So to have less error, like we say, to have less error, you take smaller, you take better it is.
If you relate to the images, particularly the graph of the images, so you have to it is the regular pixel of the image. So you will take those markers and you know the consider those reflections and it gives a linear level.
Okay. So the key point before I move further, key point is that here I am giving equal weight to all the squares regardless what fraction of the object are contained in that square. So equal weight given is not fair. So I am going to be a little bit fairer now. So that to do that, we invoke the idea of multifractality. So what is multifractal? How does it differ from fractal? Because as I say, this is a generalized theory. So if you know multifractality, then you know also fractal. We'll learn more. So you see, at what point do you think that your system is a candidate for multifractal description? Well, as a point, you see that gold, for example, is not distributed on Earth equally. Some very special places you find gold in very high concentration, and few places moderately high, and many places with low densities, and very low densities you find almost everywhere on Earth. So in that case, our population on the Earth's surface are also distributed sparsely, wide fluctuation. So in Bangladesh, India, for example, density of population is very high. Go to Australia, density of population is very low. Okay? So under such circumstances, it is better to go for multifractal description. What do we do? So if you have an object or object means what? You have some constituent. Or population. So you measure the total population and you put a grid and find what fraction of the object mass contained in that rest. So that sum over pi will be equal to 1. So pi means it's a probability. So if I know I want to be fair, so if there are some low concentration, so I put in a weight. So I pi to the power q I measure. It's called, in the multifractal formalism, this is called partition function. So I construct a partition function and I measure this quantity by varying delta. Delta is the grid size, square size. So, and we find that exhibit a power law. So that q decays with delta size of my tuning parameter following a power law subject to the constraint. The exponent tau q, you see, if q equal to 0, then this becomes number n. And n grows delta to the power minus something. So previously we saw that exponent is nothing but fractal dimension. Indeed, tau 0 0 has to be the dimension of the object. So skeleton, where the constituents are being distributed. And tau 1, if q equal to 1, tau 1 will be equal to 0. Otherwise, it is required by the normalization condition. Okay?
Sir, I have a question.
Yeah.
So, when we are reading the partition is nothing but a set. But here you mentioned that this is a function. How you can define this partition?
In thermodynamics, you mean?
No, even Euclidean space. So, when we treat the partition is nothing but a set. We have all those points and form a set. Suppose you have, for example, in Riemann integral, so we are calculating the area of under the curve. So we can have the set of points we separate it, and then we minimize the. So if we want to increase the numbers, so then we can get more number of points. Then we can compensate the part. That's the partition. But here,
Nomenclature doesn't matter here. They just it has no connection with the thermodynamic partition function or any other partition function. But they call it, okay, if you can call it even generating function. More generalized is a generating function. You see, in quantum mechanics, in mathematical physics, we solve equation. It's a moment kind of QF moment of PIs, basically. QF moment. But since in the formalism they say partition function, I often call it partition function. But reluctantly, I'm not doing it. Yeah.
So is it different than the general definition of moment, or both are same, how we can relate the definition?
No. Moment is a universal definition. You see, if you have a distribution, you take the qth power and you add them, always it is a moment. So it is the qth moment. Okay? So now I want to go a little bit deeper into this problem. So I take log on both sides. Then I find tau q. And derivative of tau q with respect to q give a better understanding of the system. For example, if I take a derivative of this with respect to q, I get this one. And you see, when q equal to 1, this quantity, you know that minus pi log pi is Shannon entropy. So you can find the entropy of the system as well. That means the little squares that you have, how many ways you can arrange them. So that's kind of disorder also. You can measure entropy here. The most important point that I want to mention here, you see, if you have pi, some cell, ith cell, has a amount contained in the ith cell is bigger than pj, a jth cell, then as you allow q tends to infinity, that simple inequality becomes, so pi to the power q, you get the discrepancy is much bigger in the limit q tends to infinity. So all the squares you have, then you see which squares have maximum content, and you highlight them. Their value is so dominating compared to the other, so you can ignore them. So in the sum, only those which has maximum amount of content will dominate the sum. So I can say n number of square I have, which has maximum p's. So I can get, and I find that p plus is a maximum, the squares that contain the maximum amount of content, fraction of the mass. So that scale like this. On the other hand, if pi is less than pj, then this one get bigger, pi contribute more. You see now by q as q tends to minus infinity. So in some cases, I can make even the smallest one contribute by considering q tends to infinity. So in that case too, I find p minus delta to the power scale like that. So I can now generalize the case. P's scales with delta as a delta to the power alpha. Here alpha is called Holder exponent. And one of the property of the tau q, you see, always this. So in the limit q tends to infinity, positive infinity, I put alpha minimum. Why is because as q tends to infinity, slope is minimum. As q tends to minus infinity, slope is maximum. That's why I put alpha minimum and alpha maximum. So now I go by indexing my squares in terms of I. Now I have a Holder exponent. So I now index them as a function of alpha. So I transform from a sum to an integral. But with the price I have to pay, I have to add the number of cells, number of cells which has same alpha and delta. So and then as I know that pi is equal to q to the power alpha, so pi to the power q must be delta to the power alpha q. Now tau q can give us a better physical significance than, sorry, if I make a Legendre transform of tau q, that Legendre transform can give us a better interpretation of physical interpretation than tau q itself. What does this Legendre transform means? Because here tau is a function of q. Instead of a quantity that depends on q, transformation means a method by which its derivative becomes the new function is a function of its derivative. So it's a simple way. You all know that how to get internal energy. So internal energy is function of thermodynamics, function of is entropy, but entropy is not a measured quantity. So we go to free energy by doing the Legendre transformation. You see also Hamiltonian is also Legendre transform. So Legendre transform is very handy thing that gives a better physical significance. So if I do that, then I find tau q is equal to f alpha minus alpha q. If I put it there, then I find this one equal to delta to the power alpha q, which is there, and n scale like this, n scale like that. We know that when n exhibits power law with delta, the exponent is what? Is always the dimension. So, but only difference is that now the dimension is not a unique single quantity. We have a spectrum of dimension, and hence the name is called multifractal. Okay. So, how do you know that polynomial system is a multifractal? If tau q is non-linear in q, then it is multifractal. If you apply the formalism to even a fractal, you will find tau q is linear. When tau q is linear, you know for sure that your object is a simple fractal. If it is non-linear, we'll check some of it. The other thing is that second derivative of f is always less than 0. That means the curve is always a concave. So one of the universal features of the f alpha spectrum is a concave curve. We'll apply. We know that Cantor said the most simplest possible fractal. We will apply the multifractal formalism in this case. What do we do in the fractal? Cantor said we start with a line of unit length. We divide into 3 equal parts and remove the middle third. And we keep doing it over and over again. Finally, the product that you find, you see that point dust, you will have dust, but this time dust are not sitting along a line in uniform fashion. If it were uniform, the dimension would be 1. But you see, there are huge oceans, but there are no object. There are gaps of all different sizes. Okay, so the number at end state is 2 to the power n. The size of the interval at the end state is 3 to the power minus n. So if you eliminate n in favor of delta, you find that n decreases following a power law with the delta. The exponent This is always the dimension. And this time the dimension is log 2 by log 3. See, now the object is, this is the object embedded in a space. Which space? Dimension 1. So an object is a fractal if its dimension is less than the dimension of the space where the object is being embedded. This is unique definition. There cannot be any better definition than fractal. So then this one. So one important point. Next important point is that fractals are always self-similar. Self-similar is a kind of symmetry. And Noether said, Emmy Noether, a German scientist, Noether said that for symmetry, you must have a conserved quantity. What is the conserved quantity? You take, what is the size of this? 1 by 3, 1 by 9, 1 by 27. Or say this one, 1 by 9. So 1 by 9 to the power log 2 by log 3 plus 1 by 9 to the power log 2 by log 3 and this add, then you get equal to 1. And also you do the same thing. This to the power log 2 by log 3, this to the power log 2 by, and you add them, so this is the one conserved quantity, regardless of the value of n. Which step you are, doesn't matter. At all steps, this sum is a conserved quantity. Now, if it is a conserved quantity, then I can consider this as a pi. So I define this as a pi. I construct z cube, it's take the cube moment. And I do a little bit of algebra. I find it exhibits a power law. But this time, the tau q is linear in q. As I say, if the tau q is linear in q, it is simple fractal. In this case, tau q is linear. And if you do further calculation, you find alpha spectrum is a unique value, df, unique monofractal, or one fractal, one dimension. I apply the same case, for example, in a two-dimensional case. Now, if you start with a square, you divide into 4 equal parts, and you remove the top left square. So, we find after, if you continue doing that, you find number goes like 3 to the power n. So, in step 2, there are 9. In step 3, there will be 27, and so on and so forth. And if you, again, delta is 1 by 2 here, 1 by 4 here, 1 by 8. So it is 2 to the power minus n. Again, if you eliminate n in favor of delta, you find df equal to log. So this one has a fractal dimension is log 3 by log 2. Again, if you take sum of this, is a 1. So there is again a conserved quantity. All fractal must have, whether you can identify or not, it must have a conserved quantity because it's similar. Sometimes it is very difficult to know which is the actually of conserved quantity. But in this case, because case is simple, finding the conserved quantity is also simple. So again, we call it this pi, and we again apply the same formalism, and we find tau q is equal to. So when it is a fractal, this is a universal relation. The tau q is equal to 1 minus q df. It obeys the constraints that I mentioned earlier. That tau 0 equal to tau 0 is the dimension of the object. Tau 1 equal to 0. So it obeys all the constraints that we had mentioned earlier. Yeah.
So the conserved quantity is only a consequence of the self-similarity.
This is
so that holds for the simple and for the multifractal.
Multifractal.
That I got it.
Yeah, I'm going there. Yes, you will see that.
Oh, okay.
It's a good point. Now, the same thing, I can do a multifractal here. So, by dividing into 4 pieces, instead of throwing the top left, I paste it here. Now, you will understand why it is multifractal. This one will be multifractal. So, after step 1, the concentration of each square are not same. It has mass equal to half. It has mass equal to 1/4. It has mass equal to 1/4. If I do it again, it has mass equal to P1 square. So I have highest mass, intermediate mass, and lowest mass. So if I continue, there will be some holes. But those squares, not all the squares have equal weight. Mass are different. So when you have different masses, that is a candidate for multifractality. So now in this case, you see, kth type of mass. When k equal to 0, you have k equal to 0, so P1 to the power n. So if you n equal to 1, then P1. And how many of them mass? So if k equal to 1, you will have 2 n1 equal to 2 here. So this nk will tell you how many masses of kth type, how many squares are there of kth type, and this is the mass of the kth type of. Now, if I take the moment of this with the appropriate normalization condition, and then I can construct the partition function. And by simple algebra, I can find tau q. And this time tau q is not so simple. It is non-linear in q. This is no more tau q is linear in q. So it is a multifractal. And again, you see tau 1 equal to 0. You see q equal to 1, p1. So at any stage, p1, whatever the value, so total mass is conserved here. Because I have not thrown anything away. I have cut and I have pasted. Right? So this, and this is the F alpha spectrum with a concave curve. So now we have a spectrum of dimension F alpha. Each of them is a dimension. That's why it is called multifractal. Okay. I can apply this also square construction of a square, and you see again it's linear. So if it is square, doesn't matter. Now I'm now coming to my subject, what I propose. You start with a square. How much time do I have?
10 minutes.
Only?
You can take it.
Don't stop.
It's okay.
Oh, you're so kind. Can I? Do you all agree? Thank you very much.
We started late. No, please.
Thank you so much. Thank you. Okay, great. Good. Yeah. So now I start with the square of unit area, unit mass. Instead of creating a square lattice, I asked myself in 2010, what if I cut them randomly into 4 pieces? Like this. I started with a square of unit area, unit mass, unit length, everything, and then randomly into 2 squares. And so just to ladle them, I made it clockwise, 1, 2, 3, 4. And next step, I pick one of the 4 squares, preferentially with respect to their areas. So the area which is bigger is more likely to be picked. So A1 plus A2 plus A3 plus A4 is still equal to 1. So this area is like a probability. So according to this area, I pick one of the square. So it's, for example, I take this one here, and then 3 become redundant. So I randomly divide into 4 blocks, and I top left corner I recycle the 3, level 3, and then 5, 6, 7. And I continue doing it. And thanks God I have a computer to do this for me. And the picture look like this. Okay? After t equal to 1000 steps, t is the time. Now I can describe each square, each block by their length and then size. And then I say, what fraction of the total blocks has area, sorry, length x and with y. And how does it evolve with time? So this f evolved with time following this. So you see, I picked one of the square proportional to the area, right? So once I pick a size of x and y and I divide, my counter del by del t, he is watching, because it's evolution, he's watching, then that is lost. And that's why the minus sign is. And those squares has a bigger than x1, x length, and bigger than y length, I can break and I can create of size x. And that's why that is a plus sign, and all the 4 blocks that I create, any of them can be of x and y. And that's why factor 4, and this y1 has to be bigger than y, and because 2 had the gain term. So this is how, this is beautiful equation. If I did not know this equation, I would not be able to solve this problem and reach how rich the problem is. Apparently simple, but it's, so I can take the moment of this is called Millen transform, and I can plug it there, I get a simple equation. That simple equation immediately tells me that when n equal to 2, n equal to 2, dm2, this derivative equal to 0. Meaning m22 is a constant. Of course, it has to be constant. But is it because this is the area? Total area is constant. If I sum all the blocks, m22 is nothing but the total area. You see, when I put m2 and 2, this is x and y. Summing all the areas with the appropriate normalization factor,